just wanted to break the ice with you guys, like showing a little bit like what I have done before and stuff. Mael, you want to?
I have a slide right after yours.
Okay, perfect.
You can, yeah, put the text, sorry. Yeah, so my name is Maël. I'm from France, from Strasbourg. I lived there for about 10, 12 years, moved to Switzerland then with my family. And that's where I started my studies, initially in economics. And then I moved on to a master's in actuarial science. So it's like statistics applied to the insurance sector. I tried to work in this industry. I didn't like it. So I ended up doing a second master's in data science this time. So that's the point. I moved to Paris for quite a bit. And after that came the question of what do I do with my life? And so that's the moment I figured out that I would travel for a few months. So that's a bit of a map of the stuffs that of the places I traveled to at that time. Really liked it. So that's like a picture of some of the waterfalls in New Zealand, and so also like a boat in French Polynesia. And then I started my PhD at EDIAP and EPFL, which is a bit less exotic, but it's also cool. And I'm working specifically on the applications of speaker identification, which we'll touch upon today, in criminal investigations. So if we collect data from law enforcement agencies, how can you detect who's the speaker, and how can you build relevant criminal networks that actually carry some important information for investigators? So that's yeah, mostly what I'm focusing on during my PhD. So one.
Okay. Oh, sorry, I did. That was
yeah, sure. That's fine.
So yeah, well, this is like a brief outline of what we are planning to present. So there's like an introduction in speech recognition, in speech processing, sorry, and also we are going to talk about like more or less our like specific areas, either speaker verification for Mael and me in speech recognition, automatic speech recognition, and then we are going to see how to build a voice assistant that like embeds three specific areas, like which is speaker verification, automatic speech recognition, and also an NLP like NLP task. And so on. So these are a couple of links to a resource that or information like things like we would like to share with you for this workshop. So it will be good if you I'm going to put it maybe 1 second in the link in the chat. So it will be nice if you maybe start if some of you haven't done it, maybe if you do it, that would be great. So to everyone, right? Or can I send something to everyone? Sorry, like maybe here. If someone like it's on GitHub repositories that we will be like yeah checking later. So it will be nice if you like maybe can take a look to that later. So okay, so let's start. So okay, this here. So I'm going to start first with the part of speech processing. So there is like a motivation of this that like speech processing and all things related to audio processing, yeah, related with the speech task are becoming like very like important in daily life, even though like most of the people are not aware of this. So for example, we see that in voice like biometrics for access management or like voice assistants that you can see like also for cars, home automation, like I don't know, Siri, Cortana, and all these companies working on this. So it's like getting a field very like with a lot of interest from the research and also industrial area. Yeah. So for example, also you can see that speech-related task for COVID identification, like starting from the speech. So also recognition of commands and keywords. Let's say that you want to use, I don't know, your iPhone or your phone for calling someone. So sometimes you just say, please call this. So then you are doing like a kind of like recognition of a specific commands. So that's some type of task that you might see. So, but also we have seen that the ASR part of this part of in general of speech related to speech, like speaker verification or things like that, is like kind of a missing block in NLP applications. So what we'll like to present here and show you is like we like to like dive a little bit deeper in these kind of speech technologies, like so then we show you what you can do, because sometimes like like due to that we don't know, like people maybe don't know like these things exist, then you don't like are not aware of this. So we want to show several like tasks that you might do with this, and also understand the basic of a speaker and speaker recognition and automatic speech recognition. Oh, sorry. And also we'll show some libraries that might be very useful for you in the future if you want to dive deeper in a speech related task. So first of all, we would like to present a bit of some basic of audio processing. So we have two things, like we have like the audio or the sound wave, which is a vibration that is created by a local pressure deviation from atmospheric pressure. So we have this information, and then we can use like a microphone to record this information and to transform this information from the the environment, like getting this information from the environment to record it in the and put it in a analog way to record this sound wave or in an electric signal. So then we can also, then we have this analog signal that needs to be needs to interact with, let's say with, for example, if we want to train an ASR system, we need this data somewhere. So what we do is that we do this conversion from analog word to digital word, and then we can use that information for different speech related tasks. So for digital audio processing, we have that there are different features or things like can define a specific let's say recording or speech, for example, like the sampling rate, and depending of these features, like normally some tasks are more affine to different features. For example, telephone speech is 8 kilohertz or things like that. So depending on the task that you will be using, you will have like different features in your data. So also an important thing is that some of the time we have, like, for example, there is like different audio channels and things like that you need to be aware before start using that. For example, in my area, there is speech related, like ASR for air traffic control. Sometimes you have like two different speakers. So in this case would be like the air traffic controller, and also would be like the pilot. So sometimes when they are talking, they use most of the time different channels. So you need to know, like, for example, how is this information in the data before starting to interact with it in a different application, let's say. So as like this is like mainly about the speech, it will be good to show you like what in general is a speech. So it might look like easy, but it's very complex how a speech is produced. So normally you have air in your lungs, so you push that air out, and it goes through the vocal cords, and the fastest this air comes out, the louder the sound it is. And also then that way you can, like, using the mouth, the nose, the mouth, and the throat, you can produce different sounds, and let's say like phonemes or things like that, and then you can produce words, and then that's when you produce a speech. So as you might see, like there are a lot of like some organs and different things like involving like the production of a speech. So that means that a speech it can carry a lot of information, more information that what it actually actually looks like. So starting from that, like let's say that we have a speech, then a lot of things are involved there, then we can get a lot of information from there. So that means that we can get, for example, linguistic features. For example, let's say that what is being said, that could be like okay, like what I am doing that now, like just saying something. Also, you can identify what language is being spoken. Let's say that in this case is English, but it could be Spanish, and as in the previous presentation, you saw that there are like around more than 7,000 different languages in the world. So it's like you can also identify that. But also you can identify like this kind of paralinguistic features. So let's say that you can know who is speaking, the accent of this person, because you know that you have language, but you can have different accents. And for example, me and most of you that are coming from South America, you know that each country has different accents. So things like that can be identified through with the speech. Also the gender, age, and different things. But also you can go like to emotion recognition, and then you can go like more granular level. Let's say you can see the stress level, cognitive, depression, sleepiness, and so on. And also you can get some like information like speech pathologies. For instance, in the research institute that we are working, there are like PhD students and people working in these kind of things, like pathology that you can detect with the speech, and how you can help people to just to identify this in an automatic way, and how you can act later. So then we have all these kind of information that we can get, or we can get from speech. So there are different tasks that you can do. For example, a speech recognition, which is also called a speech to text. You are going from a speech to text. Also language identification, speaker recognition, accent identification, gender detection, and so on. And new tasks, like for example COVID detection with the speech. So it's like it's not like a very like a constrained field or whatever, but there are like different things like you can experiment and also mix to get. So, but also another important thing is that it's also a generative task. So we can do, for example, a speech anonymization or a speech synthesis. For instance, I was explaining this part of my project, which is the air traffic controller talking with the pilots. So sometimes when they are talking, they say some information that is personal information. So sometimes you need to address that, because with all the regulation that you have been seeing, like for example in Europe and also in America, about like a privacy and things like that. So then you need to how to target this, how to, like, if I do this task related to a speech, how to anonymize that. And also, for example, speech synthesis, like how you go from a speech, from text, sorry, and then you go to a speech. So there are like a lot of things that you can do with a speech, and it's kind of related also with the text. So to get started with the speech processing, after this, you will get the slides. So there's a couple of links that you can follow up if you want to, follow up more in speech related things, and like go more theoretical, how to approach this area and so on. So it's also, as I mentioned, like for a speech and all these kind of related tasks, we need some we like to present some libraries that are really important for example, for speech manipulation SOCs. So let's say that some of these systems that, or pre-trained models that you have, maybe you might have seen in from Hugging Face, Facebook, like developing Python and so on. Sometimes you need like a specific, let's say for a speech recognition, your system works at this like a frequency, like sampling rate, like a specific sampling rate. So there are some libraries that allow you to, for example, split the data or pre-process the data needed for this system. So some as those. And also we have seen a growing interest in the speech in general. So there are different libraries like Caldi, Speech Brain, which was released like 3 months ago, and also Hugging Face, who is working in democratizing this, all the machine learning, AI, and things like that. So basically our tutorial will be developed we rely mostly in a speech brain, which was released 3 months ago or so, and is mainly developed in Python and PyTorch. Is written in Python and PyTorch, with some interface with Hugging Face and also with Facebook AI research, where you can get pre-trained models and things like that. So we will go like deeper in as the tutorial goes through. We will explain how you can, for example, develop and also deploy an ASR system and a speaker verification system and so on.
And maybe a fun one to stress out is also that there's been a growing number of libraries that are easy to use to get introduced to speech, and that's really a chance that we've had lately for that. And this kind of tutorials would have been completely different if it were done 6 to 8 months ago. So it's something that's evolving really fast. Lots of models are being added all the time. So I think it's also an exciting time to get into speech processing. And the fact that Hugging Face is pushing into this is also, I think, something very cool.
Yeah, that's true. It's as you mentioned, like maybe 1-2 years ago, it would have been maybe a totally different tutorial. Yeah. So as he mentioned, it's like a very exciting time where to start on, as I mentioned, never is too late to start. So this might be the ignition to continue in this area. So also some notes that I want to share with you before continue is normally for automatic speech recognition, that is going to be my part, and also maybe for speaker verification as well, and some of the speech related tasks. Normally you need a large amount of training data to make a model to converge to do with a good performance the task that you want. For example, speech recognition, do a translation from speech to text, or a speaker verification or things like that. So normally you need a lot of data. So if you need data, that means that you also need good computing resources. So most of the times, for example, for speech recognition, one GPU cannot solve, you cannot reach the at least for, let's say, the performance that you want in a pertinent amount of time. So that's another thing that it's important to keep in mind. So that means that you need a lot of patience, some time to for example, to train. The training of these models can take even weeks. And for example, for Facebook, one model that they released 1 year ago or so, it took it could take a month. So it's important to as the time pass by, the models grows more, and then it's more computer resource that you need. So for example, as I was explaining, this system from Facebook, it's called Bath to Beck. So it's massive, and it takes a lot of time to train. So however, if you have that model already trained, then you can use what is called evaluation or inference in a CPU, which is what we all of us have now. If you're watching us from a computer, you for sure have a CPU, and you can use that CPU to do inference, or let's say to do speech recognition, or do a speaker verification, or do NLP or things like that. So then we will only interact with pre-trained models. So those models are the ones that we shared before in a link, or are also in the GitHub repository that we sent beforehand. So this, as we mentioned, we are going to go with SpeechBrain, which is developed by Mila Montreal in Canada. So it's basically an open source, all-in-one toolkit based on PyTorch. So what this means, okay, previously we had we used to have, or we also have, we all keep working with these different libraries, but before it used to be different libraries for different speech related tasks. So the idea of SpeechBrain is that, okay, makes sense. If I am using, if I am kind of developing systems based on speech, that means that we have different tasks that have one common idea, one common core, which is the speech. So why not you developing everything in one toolkit to do these different kind of tasks, as you can see, speech recognition, enhancement, separation, and end-to-end also language understanding. I imagine that in the future will be something like machine translation if you want to go like directly from English to, I don't know, to Spanish, like end-to-end. That also would be like will be add there. So then there are many functionalities and pre-trained models. So you just need to like if you do this, they also release this in the PIP. So you can just do PIP install SpeechBrain, and that's all what you need to start like doing ASR and also applying like the task that we are showing there. So for instance, if you have like when you have, if you like out of the box, how it works is like they have for ASR at least, they have a class which is called encoder decoder ASR, and then you can get from either Hugging Face or also Facebook AI research like these pre-trained models. Like normally they are big models, but state-of-the-art models, which means that they are pretty good. And then we will teach you today how to use it and how to evaluate, for example, in your own data and things like that. And they also show like ways how you can train your model. Of course, you need compute resources and things like that, but that's something that you can start like checking around. For example, for instance, there is this common voice data set, which is around more than 600 hours of French. And then they show like a step by step how you can do like all the ASR and speaker verification and things like that. So it's we definitely advise you to go there and check it out. So for instance, if you want to train a system, you just need to define some or change some variables that you have there. For example, your own data. Let's say that you have tomorrow, you want to add this part of ASR in your bachelor or master degree project. So then you can use this high-end toolkit to do that. And then you will need to just to modify a few files, and that will be enough for doing a speech recognition or things like that. So yeah, now I leave you. This is the second part of the tutorial.
Yep. If you don't mind, I'll share my screen directly.
Yeah, it's better. Just wait.
Okay. So I'm just checking if there was any intermediate question that we could take now. So do you see the question, Juan, also?
Yes, there was a question. If you want, let me read.
Yep.
Well, the first one, I think you already answered, right? The speech brain can be used with Spanish, and I say
it can use with the Spanish. It can be used with the Spanish, and there are several languages. Miles was mentioning maybe to me like 1 month ago. They had this special kind of event when they were developing like different ASR for different languages, right?
Yep.
With Hugging Face and Speech Brain, so you can have you can find many languages there. So.
And the other one is from Selene Baez. She says, does end-to-end spoken language understanding focus on instructions only? I guess so, since it is developed for personal assistance, does it also extract other factual information similar to the task of information extraction when working with text? You want?
Yeah, maybe I can take this one, and Juan, you can bring something on top. So we'll dive in the ASR part afterwards, but all end-to-end models are like work just like the encoder decoder models that are quite common in ASR. So just consider that they can sort of do the same speech applications than the rest. So they don't only focus on instructions, even though that's something we are going to be introducing there today. But you can do, if there's transcripts that you want to generate from a conversation in live, that's also something you can do.
Yeah, basically there are different like subtasks also in just like in the area of speech recognition, and also it depends. For example, if you have these personal assistants, they also do like speech recognition and things like that, but they also, I mean, leverage this speech recognition thing to do like a more granular things, like just like commands or things like that. So let's say that you have the backbone model or something that is working, like it's maybe core for all the same like specific task, but then you can somehow like differentiate it.
Yeah. So I hope it answers the question.
Yeah.
I have another question, guys. Sorry.
Yep. Go ahead.
From the YouTube channel, no Sabri says that can I build a model to recognize Arabic voices, and what would be the best steps to do this? I guess well, this is part of the tutorial, right?
Yeah, not in Arabic for the tutorial. We'll focus on English. but yeah, sure. So you can. I think the best way to start would be you have this huge chance now that you can start with Hugging Face pre-trained models for Web2Vec, and Juan Pablo will probably talk about Web2Vec shortly. But basically, there was just a framework that is said to be as much as a breakthrough than BERT was in NLP before. So you can, there's many languages that were just say to be low resource languages. So meaning collecting thousands of hours of training data was hard. I would just start with any pre-trained model that you can find on Hugging Face. Usually the way it's done is that there's a big library, like big data sets named Common Voices. That's usually where you could start, and it's already embedded in the dataset library from Hugging Face. So just following the tutorial, either to play around with the model, or you can retrain the thing on your own data in not too long. So that's basically where I would start, especially for languages, depending on the sub-language you're interested in, where it might be you might be limited by the amount of training data that has been collected and annotated. You just also have to see that the annotation of such data takes a huge amount of time, and sometimes to annotate 10 or 20 minutes of speech, it just requires several hours because you need to get the exact timestamps and everything.
Exactly. So I just share in the chat the link with the pre-trained models of Web2Vec for Arabic. So it's like they have a lot of languages there, so then you can check it out. And
yeah, and it's always a good place to start with.
Exactly.
Often, like you see the metrics that are used in ASR, but often we talk about word error rate, and the problem that you'll face is that the word error rates are still pretty high. So it's still making quite many errors that might not be ideal for whatever you want to do. And then there's the whole question of, do you have the resources to collect data, annotate data, cross many databases, or find data sets that are specific to your kind of applications that you're interested in? Because sometimes if you get data from YouTube channel, it's absolutely not the same than if you need to do ASR on air traffic control.
Exactly.
For example, because there will be different sampling rates. There will be different. We talk about like a domain mismatch in a sense, just because you'll hear lots of background noises with the air traffic controllers, and the YouTube data will be like very clean. So yeah, but it's a good place to start with, and I think you can start from there.
Yep.
Okay, I don't think there's any other questions so far. So I'll jump on to, it's a pretty short section, but I just wanted to give a brief introduction to speaker verification. And the reason why we introduced that in this tutorial is to give you an idea of another task that you can solve with speech processing, and that would not be speech recognition, which is the most common. And here, the application that we'll pursue for speaker verification is identity access management, meaning in our app that we'll make later, it will just check before running any query. If you ask for the weather forecasts, that's what we're going to build. It will just first check that you're the correct owner of the app, in a sense. So the way this is done is through speaker recognition, which is like a bigger field that is made of speaker identification. Speaker identification is basically you have a closed or open set of speakers, say 10 speakers, and you have one new recording, and you want to say who does this voice belong to? And so it's like a multi-class classification in a sense. And when we talk about open set speaker identification, that also means that you have one additional class that takes any speaker into account in a sense. So that could be any of the 10 speakers, but also someone else. So that's for speaker identification. Then there's the part of speaker verification, which is the part we're interested in. You have an initial recording of someone speaking, and you want to know whether this is the same person that's talking again now. And so that's speaker verification. And then you have the task of speaker diarization. Basically, speaker diarization is sometimes when Juan Pablo presented the, when you have the mono or stereo files, when you have mono files, that means that typically for telephone speech, you would have one speaker on one channel and the other speaker on the other channel. What it just means is you have one array with all the amplitude information for speaker A and the other with all the amplitude information for the speaker B. So that's fairly easy because you can just say, okay, I know when is speaker A speaking, when is speaker B speaking. But sometimes you only have one channel of recording. That's often the case in criminal investigations, for example. And this application, what you want to do is segment when is each speaker speaking in a sense. And if there's two speakers, then you also want to differentiate. I mean, it can go quite far, but it can also go into noticing when there's an overlapping between two speakers. Yeah, but the whole point is just to segment into who speaks when. So why do we need speaker recognition? We've introduced some of these concepts, but basically block or grant the access to a service, for example, like a banking service. I've seen some of these applications. It's not the most common though. Like usually it goes, like for example, face identification is a bit more famous in there. Activate voice assistant with your voice only. I think that's the most common application that we can see. For example, if I say, "Hey Siri," you don't want that to activate all of your phones because that's something that happened back then. But then that's the reason why they ask you to speak several sentences initially when you buy an iPhone, for example. Then you just need to speak several sentences so that it has your voice print in a sense. And the kind of applications I'm interested in is criminal investigations on intercepted telephone calls. So yeah, basically who's speaking on that call, because you don't have the information initially. You have the information of what's the phone number, but sometimes they use various phone numbers, so you want to match that with a previous phone number that was used, for example. Okay, so let's jump to speaker verification and how does it work? Basically, there's two big tasks in speaker verification. First is the text-dependent task, and then there's a text-independent task. Basically, text-dependent simply means you need to pronounce a given phrase to start the service and for your identity to be assessed. So that's a bit, I'd say, an easier task in the sense that you can have better performances there. And then there's this text-independent approach, which is what we're going to play with, where it's a bit more tricky. But from me talking on Zoom, for example, you also want to record that and maybe have this as my, what we call the enrollment data, meaning you store my voice print at that moment. And then whenever I access the service later on, then you need to compare like the new query that I'm making with the voice that was recorded, even though I'm talking about like two completely different topics. So the high level idea is fairly simple. You have usually 3 sources of data, sometimes only 2. You have enrollment data that contains like the recordings of the speakers to recognize. Then you have the development data. I'll come back to that later. And then you have the test data. So that's the people you need to predict the identities from. Usually when you have this, the way it would work is, okay, so that's maybe a bit detailed, but say what you have is initially, I hope you can see my pointer right. Yeah, okay, so we start with a large speaker identification database. I'll introduce some of them later. Basically, in those data, you have the audio and you have the identity of the speaker who just pronounced this sentence. You don't need a transcript or anything, but you need thousands of hours of data. One of the common one is Voxelab. Voxelab was extracted from YouTube videos. You train a deep neural network model. So that's why I'm saying it's a modern approach. I'll come back to some of the approaches that were used before. You train a deep neural network model to extract speaker embeddings. The point is that you can extract meaningful representations, and speaker A has embeddings that are different from speaker B. That's your goal in a sense. Once you have that, you extract speaker embeddings for all your enrollment data and for all your test data. So you have, say, 1 minute of enrollment data for speaker A. You extract the speaker embedding, so you have this vector. Then you extract the embedding for the test data. So that's the new U-turns that you would collect for speaker A. And then the question is, how do I compare them? So the way you would compare that is once you have an enrollment data, we talk about a speaker model. Basically, the embedding that you have for the speaker is named the speaker model, which is basically like the vector that represents the voice print in the sense of the speaker. So the question is, how do I compare this embedding with this embedding? And there's several approaches to do that, but basically you'll solve a classification task, accept or reject. And then you can also extend this to what do I do when I'm doing a speaker identification? It's not only classification on 2 classes, but I'm also looking at many potential speakers. So here, everything that is related to extracting meaningful information, so speaker representations is named the front end, and then you have the back end, which is the classification task that you solve on top. So let's first get started with how do I train a neural network model to extract meaningful speaker embeddings? I think there was maybe 1 or 2 questions that I can take. Okay.
There are a couple of questions. Maybe I can answer the first one.
Yep.
So, well, it says, what are some free access sources where one naturally can and continuously can scrape or acquire speech data? So, for example, we have seen that in our research institute that the one common way is to do web crawl. So basically, you, for example, you can do it from YouTube and download a lot of data from there, which is normally open source. And then you can get this data, and you can also filter by languages and things like that. Also, I mean, depending on, for example, the title of the video or description of the video. So then you know that if this video is I don't know, like a description is in Arabic, that means that maybe it's in Arabic that, or maybe then you can use like language identification system to detect if where this is Arabic, and then you can download that. So normally, in reality, what it is not like what we see that we have a lot of databases for speech, but what it's like the background is that there are a lot of things like that you are filtering. For example, when you download this data, then you filter which is the data that is very noisy. Then if it's not the language that you are looking for, then you also like then you can also delete what is noise and what is silences, and then what you are really interested is in the speech part. So that's something that you can, for example, do in a speech brain or the system that we will be presenting. I hope that answers.
Yeah. And Juan, do you mind reading the second question?
The second one is, can a single model verify the same person speaking a different language? Or will we need to model a speaker A Spanish and a speaker B English as separate speakers?
That's a very good question.
Yeah.
So what you would see typically is that you have lower performances on multilingual frameworks. So when I have, for example, in the investigations that I process from time to time, when I have a speaker that's speaking Arabic and then English, the performance of the model is degraded. It doesn't mean it's not working, but it also means if you can extract one embedding per speaker per language, that's also better. So if you have the chance to do so, that's a good way to go. And otherwise, the speaker identification models, like the feature extractors, are also trained on multilingual representations. But it's just that the embedding that you extract for one speaker is better.
Yeah, just to answer maybe the same thing for speech recognition, it's more or less the same. You can train like multilingual speech recognition systems, but sometimes you have like a less performance when you like training that in such way sometimes. So yeah.
Yeah. Well, thank you guys for the question. That's
I have a couple questions from YouTube. If
Yep.
cool. Yep.
so, the first one is how about the correction aspects? For example, if I need a system to give me some feedback regarding the spelling aspects, right, and spot the errors. I mean, I think
it's about like, how do I correct the transcripts made by the speech recognition system, or am I not getting the question correctly?
Yeah, give me a second, because I think this is a continuation of something. Yeah, because the example is, for example, you know, the Quran recitation needs some specific, I think, some specific spelling, how to pronunciate, right? Some words.
Yeah.
And
I think we can skip that question for the ASR part for Juan Pablo, because he'll touch on like language models and stuff like that, and really go in this direction.
I think in the same direction is some question from Ilaria Cruz, that how do you prepare speaker embeddings? So I think
that's what I'm diving in now. Yeah.
Okay.
Okay, cool. Okay, so I'll start with like what's the most commonly used as a speaker embedding extractor. So the task is basically that you train a deep neural network to classify speakers on a very large database, and then you only use the final layers of the network as a feature extractor rather than just using the classification itself. So why is it a hard task? And I think you can pretty easily see that. It's because we have enrollment data with variable length, and that's the whole thing with speech processing in a sense. It's when do I know when it starts and when do I know when it stops? And this whole thing makes it tricky. And so you need architectures of your deep neural network that can capture temporal information and somehow average them. Also, it's a very hard task because if you ask humans to recognize voices, they cannot understand a lot of voices or recognize a lot of voices, and it just requires a lot of training data. So the way it's done is basically you train a deep neural network with a temporal pooling layer. Usually that's named a TDNN. It's this sort of architecture, like a tree-based architecture. The point is then you just have from like in the proposed architecture that is named X vectors. So X vector is like the speech representation, like the speaker representation that you can take out of a speaker for every time frame here, so that you take segments of a few seconds to a few milliseconds, and you will just have pooling that is being done over them over and over again to capture a lot of temporal information for each of the classifications that you're doing. So if I jump a bit more into what's the input and what's the architecture. So an important part is data augmentation. So it would be reverberation, echo, that would be babble in the background or like noises. These models are subject to like a huge performance improvement if you do data augmentation. So it's one thing you can do in SpeechBrain, that's one thing you can do in Kaldi also. Then you extract usually what's named MFCCs, so 24-dimensional filter banks. Basically for each segment of 25 milliseconds, you would extract those features. So those features do not extract information from what we call the time domain information, because that would be just the representation of speech over time. So you know those wavelets, but it extracts information from the frequency domain information. So you might have heard of the Fourier transform during your studies. So MFCCs, I invite you to look a bit more into that, but they're usually the core of the features that are being extracted. And you do a sliding window over over the enrollment speech. The model architecture, in a sense, is you have first the speech frame level layers. So that's the initial input that you have to the model, so x1 to xt. So these are your MFCCs that you put in, and then you have stat pooling that goes on, and then you talk about not a frame level, but a segment level, because the frame level is just 25 milliseconds every time. But then you have the segment level, meaning with your TDN architecture, you extracted relevant information over a pretty large time span. And then you have the final softmax. So the final softmax is just a probability that it's speaker I given all the input features. Basically, you don't really care about the last layer, but what you want is these two last layers of embeddings, and that's the X vectors. If I jump to, I'll come afterwards to why we use those two last layers and not the whole model as itself. But the state of the art, if you want a direction to look into, that's from its name eKappa TDNN. I think that's one of the best performing models. There might be like some that just perform slightly better, but basically they extracted better embeddings through some innovations that they took from facial recognition field. Because in a sense, you can also say that, I mean, facial recognition basically is a bit the same thing as speaker recognition, except that you have different input data. Yeah, so there's some details on the fact that the initial frame layers can be reconstructed into a one-dimensional ResNet module. They implemented skip connections. Yeah, they have a hierarchical level propagation of features. The paper is interesting, so if you want to look into this, just mention some of the metrics to see how well they performed compared to the best models from the year before that were eTDNN from Brno University from the year before. There's one challenge that goes on every year, which is the NIST Speaker Recognition Challenge. And usually there's teams that are offering some of their best performing models there. Which databases do you train do you use to train your DNN embeddings? You can use many. I'm citing the most common. Switchboard. You would have also NIST. NIST is by far the most common. It requires a license, so usually that's through your institute or through your company. But it's been running speaker verification challenges since 2000 something. I mean, basically you have more than 10 years of data, and every time there's thousands of speakers. So yeah, and Voxelab is the free version. So it's YouTube content, and they've made those classifications based on the YouTube channel. And so you can see in terms of hours that you would get the SRE from 2004, 2006, 2008, 10, etc., etc. That you can also combine with a with a switchboard, and usually you just sum those databases. So you take many of them to train your data, because you want to have a diversity of data when you train your deep neural network embeddings. But you can easily get to 10,000 hours of training data, which is why doing this kind of a computation on a single GPU becomes quite heavy from time to time, and you can pretty easily spend a few weeks training these models, and hopefully there's pre-trained models that you can play around with. So what do these embedding captures? That's a paper I really liked that looked into, in sense, if you try to make out of the embedding a classifier of what is the ID of the session, because the session would be simply a recording session that has specific parameters. There's the reverberation of the room, there's the microphone that's being used, there's the distance from the speaker to the microphone. Can you classify what is the ID of the session with the speaker embedding? On average, you can do that with X vectors around 35 to 40% of the time. More interestingly, if you look into speaker gender, the gender is highly predictable from the speaker embedding. So you would expect to have more similar embeddings for males that have, of course, similar voices, but like for two males rather than for one male and one female. The speaking rate is also highly predictable with the X vectors. A quick word on what happened before deep learning. So that was the X vectors. So as you can see, it's just you have a bunch of input frames. You have a TDNN architecture with this time delay sort of a hierarchy where you pull the information from frame level to segment level, and then you just focus. You make the classification with you're interested in the probability that it's this speaker given all the input data. And every time what you do is you just take the final layers. But so what happened before deep learning, just putting some resources there. The point is not to go too much in details, but we had something named UBM GMM, so Universal Background Model, Gaussian Mixture Model. The point was you extract MFCCs, and then you model the various frames of speaker using high dimensional GMMs. Yeah.
Sorry, I think it is my connection. Sorry, go ahead, Maya. You froze for a moment. Sorry.
Okay. Yeah, if that happens again, just tell me. It might come from me. Okay, and so in the UBM GMM, in a sense, what you're interested in is classifying the probability that it's the given speaker that is speaking currently versus the universal background model, which is basically any other speaker that you have in your enrollment data. So like a very generic speaker representation. And if you have your hypothesis, H0, which is this speaker, and H1, which is this is the other speaker, and then you're interested in what's the most likely output. And that was done using Gaussian mixture models. It's really interesting to just read this if you want. Then came the GMM supervectors. Basically, you stack the means of the GMM components into a single vector, and then you can use SVM, for example, to do the classification. So that was just from the GMMs. There was 2048 mixtures for the GMM, and then you just take the means of the GMM and you concatenate that into a single vector, and then you can use any classification model that you want. What state of the art for quite a bit was the I vector. So that was a joint factor analysis that will model both the speaker and the session variability of the GMM supervector. So all these models were built on top one of another, and the breakthrough was X vectors. X vectors were introduced in if I'm not mistaken, I think it's 2018. So all of that is, as you can see, also pretty recent. Okay, so that looks maybe complex, fancy. How do I do that with SpeechBrain in the end? That's the beauty of of code, I think. You can just, from SpeechBrain pre-trained models, you can import speaker recognition. From speaker recognition, you can select the SpeechBrain speaker recognition eKappa voxelab. What that means is just it's a speaker recognition model with the eKappa TDNN architecture. That was the state of the art from last year, trained on voxelab data. Basically, that's what we want. You extract your, so that's how you read, for example, with Torch Audio, how you read your signal. So you get your signal and you get your sampling rate. And then to get the embedding, what you can simply say is encode batch with your signal, and you get a torch vector, a torch tensor that has this this size. The reason why you have 2 there is because you have 2 channel in this test data. So it will model both the channel A and the channel B, so like the left and right in the phone call. And if you want to merge them together and have a single thing, it's something you can do also. There would be no obvious application of this, but yeah, so that's how you extract these X vectors. Now comes the question of the classification part. So that's the back end in a sense. So you have these embeddings extracted for the enrollment data of the speaker, and then you have these embeddings extracted for the test data of the speaker. What do I do with that? So there's 2 main approaches. The most common is named the PLDA. The PLDA is probabilistic linear discriminant analysis. What that means is you have a very high dimensional vector. So that could be 192, but you can go up to 500, 700. And usually you apply first linear discriminant analysis to reduce the dimension of the X vector. And the PLDA is a factor analysis model that will decompose the covariance matrix. The point is to have the between and within speaker covariances to find what we name the final subspaces. The point there is just, usually you remember when I talked about this development set there. Yeah, the development data. Usually that's data that is in the domain of what you're interested in. For example, telephone conversations. And you would train your PLDA. So that's a dimension reduction algorithm, and then the classification that's being done. And what the PLDA expects as an input is just a bunch of embeddings with the identity of the speaker. And then what it expects for prediction is just the embedding, 2 embeddings, and it will just tell you whether it's the same speaker or not. Another approach that we'll use there that is simpler and that works just well for ResNet architectures, which are leveraging eCapA-TDNN, is simple cosine distance. So you can take just cosine distance between two speaker representations, and you define a threshold. You say if it's above 0.6, I'm saying it's the same speaker. If it's not, I'm saying it's not the same speaker. One step that I have not mentioned is usually before extracting the embedding of the speaker, what you would typically do is have voice activity detection, because some of the times you would, if I'm speaking, sometimes I'll make pause, sometimes I'll just speak fast. I want to remove the parts where I'm making pauses, because there I'm just capturing background noises and everything. So usually there's voice activity detection that's being done to extract only the part where you have speech. And when you have only the part where you have speech, then you can extract meaningful speaker representations. And that's just an example of how to do that in a speech brain with a pre-trained model. So we'd have the embedding enrollment. You do the same to get the embedding for the test data. And then you compute a similarity with a cosine similarity there. And you just get you have a threshold, and you just print whether your score is above the threshold. And if it's true, then the access is granted. Otherwise, it's declined. And the performance metrics, just to finish, that we use for speaker verification models. The most common is equal error rate. So that would be just the part on the ROC curve where you would have the false acceptance rate that's being equal to the false rejection rate. There's also the DCF, which is the detection cost function, which is just something where you would put specific weights or like specific costs assigned to 2 types of errors, like the fact of missing a speaker and the fact of creating a false alarm. And then you have a prior probabilities of being at the target or the non-target, and that's the probabilities you plug in there. And so with this detection cost function, usually that's what's reported in NIST SRE, and in many papers you'll see otherwise the equal error rate being reported. For if you want to evaluate a speaker identification model, it's easier. Usually it's the speaker accuracy percentage of the times you correctly identify the speaker you were supposed to identify. Okay, is there any question on this part? I hope I was not too quick and was still clear.
Well, there was a question in the Q&A, but I think it was related to some previous question. I don't know if you can see it, Juan.
Yeah, I can see it. Maybe I will read it. What about a second language speaker? How well do they recognize second language speakers of the language? To a speaker of English with non-native pronunciation, etc.
Yep. Yeah, that goes in the same direction of the previous answer. If you have a non-native speaker, I mean, there's this whole field in ASR that Juan Pablo will talk a bit more in details about. But for speaker representation, what you would typically find is that you'd find something that works probably better if it's the native language of the speaker, and that you have enrollment and test data in the native language of the speaker. And so the more custom you can be, in a sense, with enough training data or enrollment data, the better it will be.
Okay.
And there is another question from YouTube.
Yeah.
Well, the first one was, how do you prepare speaker embeddings? I think you more or less mentioned something about it. But the second question from Ilaria is, how similar is fast facial recognition to sound recognition? Well, I don't know if she refers to, I think it's image, right?
Maybe she means to speaker recognition.
Yeah, I guess it's a speaker recognition. Well, this is from YouTube. I don't know if she's interacting right now. Well, maybe we can ask Ilaria if she can clarify.
Maybe.
If she can clarify, maybe we can come back to this. Yeah.
Yeah. Okay.
Yeah, makes sense. Okay, I'm going to share the screen. So now we going to the third part of the presentation. So it should be about, yeah, like speech recognition and like more targeted, yeah, to speech recognition. So basically, before starting, I want to like as the name says, like mean is like speech recognition. What it looks like is like translate from a spoken language to text. So you go from this sequence of like a speech or whatever to a sequence of words. So, well, in a nutshell, it would be like ASR systems like automatically generate this text from an incoming audio signal who has some features and some specific things. So for speech recognition, there is like a specific, it's like specifically harder than, I would say, than other tasks. Well, I wouldn't say that harder, but you need to take into account much more things compared to other like computer science fields, I would say, because you have many variations in general. For example, let's say that social variation are like a speaker. You have different speakers, so you need to model that. So each speaker has its accents and also a style of talking, how you produce the speech. Also, there is environmental like kind of issues, let's say that noise and things like that. Imagine, for example, in my PhD research, I deal with speech from airports and also pilots. So imagine that you are in an airplane and then you are talking. You have that kind of background noise that is always there. So you need to deal with that kind of stuff for speech recognition. Also, you have vocabulary. So, for example, if you are talking in English, maybe for some specific tasks, it's different, even if it's the same language. So you have also that as a variation. Also, there are some paralinguistic kind of issues like the emotional state and the rate of speech, like how quick you pronounce, like the rate of words that you pronounce when you are talking, things like that. And there are also some issues with the, like when you want to train a system, for example, there is, it's very high dimensional input and output. So you have like very long sequences input. You normally have like how you do to get the features of, for example, an audio signal is that you have a window, normally like 25 milliseconds, and then you extract from those 25 milliseconds some features. And then you move the window like 10 milliseconds, and then you do the same, and then you do the same. So if you have a recording which is, I don't know, 10 seconds or so, then you have a lot of data. And then if you want to, let's say, convert that information and apply ASR and then get which words were spoken there, you will see that it's very long sequence. So you need to deal with these kind of things like that. Also, one thing important to stress out here is that the data labeling in speeches, for a speech like database is quite expensive, and sometimes you need like qualified personnel. For example, for in the air traffic environment, it will take like around like, I don't know, like 10 hours of one person working to produce 1 hour of a speech, like to label 1 hour of a speech. So sometimes you need to like spend a lot of money to get this label data, and sometimes you don't have that kind of option. So you need to somehow like like a engineer of a computer scientist or something like that. You need to find out how to deal with that. So, for instance, we have like, I don't know if maybe more of you didn't know that there are around like 7,000 languages in the world, which is a lot. And some of those languages just you have like you don't have the scripts or the vocabulary. They just have like you just have the information of how it's pronounced this language. So it's very like challenging to for example develop ASR systems for some of languages in the world. For instance, there is around 120 languages that Google has like automatic speech recognition. So that's just to put into, you know, to put the cards in the table, like on the table, how like what we have and what really do we need. So sometimes these languages that you don't have like labeled data, or you don't have like this kind of information, you call it like low resource languages, things like that. So some applications where you might see ASR or the automatic speech recognition is like, well, for example, there are different tasks. Like if you are like having a conversation, it's a different task that if you are, for example, reading, or if you are, for example, in a party or something like that, where you have like multiple people talking at the same time. So for different scenarios, sometimes what the research has been like kind of going is like you create a different ASR system for different tasks. Even if, so imagine if you multiply that for the number of languages and then for the number of languages, then it's like a lot of things that should be covered. So then also you have, for example, emotion recognition, therapy and pathology. For example, there is some like this like dysarthria, apraxia that affects some people and is related to speech. Also, those are some tasks that you can do with ASR. Also, virtual assistants like Alexa, Cortana, Siri, etc. Those are relying mostly on ASR. So I'm going to put some like basic things about ASR. I don't want to like to bother you with a lot of equation and things like that, but I will present a couple of equations that it would be nice if you kind of remember, or you will have like you will think about in the future. So normally what we do with the speech recognition is that we have some features of this audio, like a defined audio signal. Those features can be like MFCC, F-banks. Those are like, you don't need to know exactly the name of those features now, but you do need to know that we have those features for this audio signal. And then what we want is that we want to, given those like features, we want to know which is the most likely word sequence. So let's say that I am saying like a word and that can be translated in some features. So then what's the probability of having this word sequence? So normally what you do is like the first equation is like the most straightforward way of doing it. Like what's the probability that maximize this function, which is the probability of a word sequence given those features. But then that has been shown that is slightly difficult because of the thing that I mentioned before, which is like you have long sequences. So even if you are just talking for 3 seconds or 4 seconds, and then you want to apply ASR there, it's a very long sequence if you take it in this way. So what they do is that they partition, like they split the problem into like the acoustic part and the language model part. The first part of the second equation, they do that doing applying the Bayes theorem. So what is that is that what's the probability of those features that you have given a word, and then what's the probability of this word given previous words. So this part here in the right, as you can see, like the probability of word, that's a language model. That's what you might have seen in NLP tasks. There are many NLP tasks like GPT, PT2 and 3 or so on. That's like a language model, language models. And then in the other hand, you have the acoustic model. So that's more related to ASR part. So then, for example, for the acoustic model, what you have is like, imagine that each of these kind of blocks here, blue dot blocks, it's the acoustic features. And then what you want to do is that you need to align those blocks to a specific, let's say, letter, which is, for example, N. And that letter, there are different ways to kind of present that. Either could be letters, could be units, could be phonemes, could be different things. That if you go deeper in this area, you will see that there are many ways to represent like those features, audio signal features, to some like more like text related feature, like output features. So then for the language model part, it's like you have some previous words, and then you want to, which is the likelihood of having the next word. For example, here is like where we are going, something like that. So after all the math that I presented before, so I mentioned before, like what this equation covers is like we have the acoustic model, the language model, and we need to represent the output. So we have the input. We know that those are like MFCC features, F-band features, whatever features it might be better for your specific task. So then you need to represent the output. The output, obviously, the output that we want at the end is the words, like the word that has been spoken in this audio signal. But then you need to interface like this acoustic model with the language model. So sometimes you use, for example, phonemes or fonts or triphones, some things like that. For instance, here is an example of the 44 fonts in English. So you have different fonts, and then you need to like interface those fonts with the language model. So there is like some approaches or how to do that. I will just like explain more or less. I won't go into very much detail because it could get a little bit complex. So let's say that now knowing that, we can like put the cards on the table and say what are the main challenges in ASR. So first, the training is that we need to know, as Maya was mentioning before, you need like this BAD. So you need to know where is the speech. Like, let's say that you have a recording of 10 seconds, but then you spoke in the first 2 and in the last 2 seconds. So what you do is that then you apply this voice activity detection. So then you know where is a speech, but then you don't know where is like a specific word. So if you say like, I am Pablo, you don't know exactly when it finished I and when it finished am and when it finished Pablo. So you need to do like this kind of, you need to get that data, like that information when you are training the system. So that's called aligning. So you need to align the input data, which is these features or audio signal, with the output, which is those words or phonemes or units or letters. In this case, it's letters, let's say not right. So we need to know like which acoustic features are attached to these letters or something like that. So that's one main challenge that has been for a long time in ASR till 2 or 3 years ago. So as we mentioned at the beginning of the tutorial, like if this tutorial would have been like 2 or 3 years ago, it would have been way different. So now there are some systems that could deal with that easily. So then we have on the other hand, we have the thing with the inference. So if we imagine that you have like a huge graph or like search graph where you say like, okay, if I am saying this word, what's the probability of this word or the next word or things like that? And then if you start kind of extrapolating that to all the possible words that you can pronounce each time, it gets like super massive, like it gets like a super massive problem. So how to deal with that? There is one algorithm called beam search. You can go deeper, like delve deeper there later after the tutorial, but it's more or less how it's dealt this problem. So there are 2 main type of speech to text systems. So we have the hybrid based ASR system, which has been like around for, I would say, like 20, 30, even 40 years. It has been like there in the research area for ASR. And normally what it do is that you have the acoustic model, the language model, and the lexicon. So the lexicon is how you represent this word, like the acoustic feature, or like the output of the acoustic model. So let's say that the acoustic model is getting these audio features, then you want to represent that in either fonts, either words, either letters, or either something like that. So that's the lexicon basically. So what you do is that you, with something called finite state transducers, what you do is that you embed all that is like a separate knowledge in a big graph, and that's what you do, like that's what you use when you want to do like inference or when you want to get the text of a specific audio signal. So there are 4 like a main things, like it's in hybrid based ASR system, which is like we have the H, C, L, and G. This is the graph. Like at the end, like what you care more is like your like deep neural network model and this graph. So what you do with this graph is you go from features to words. So that allows you to interface that and to apply the ASR. So as you might see, there is a lot of different like imagine like small blocks around, like playing around, like doing stuff to do the ASR things. So one of the main issues with this system is the alignment thing, like what I was saying. Like, for example, if you are saying like your system is producing words, so then you need to know like in this like 20 milliseconds or I don't know 50 milliseconds or something, which word was that, or which phoneme, or this kind of information. So this is more or less the standard ASR pipeline. So you have at the beginning, you have the speech signal. So you need to do some signal analysis and maybe pre-processing. Let's say that you need to downsample the signal. Sometimes you have, for example, signals in 16 kilohertz or 8 kilohertz, and then your system out of nowhere just work with 32 kilohertz. So there are some libraries and things that you might use for doing this kind of post-processing. For instance, in Back2Back and SpeechBrain and most of these systems nowadays, they use signals at 16 kilohertz sample rate. So anyways, so you have this training data, and the acoustic and the language model is trained with those like with that training data, which normally should be more than 1,000 hours, but most of the cases you don't have that for a given task. So we'll come out later to how to solve this. And then you have this search space, which is this WFST that I mentioned before, and then you have the decoded test. So that's how we call it in this area, like decoding. So we do some decoding of these features to a given test or transcript. So now, on the other hand, we have the second way of doing ASR, which is more like a novel way of doing ASR. It's like how it has been doing, like, for example, in NLP and many other like tasks, which is called sequence to sequence. So in this case, sequence to sequence ASR is more recent. So what you do is that you don't have this burden or this problem of the alignment, like text alignment. So you don't need to do that because you just left the system to do it for yourself. It's like, okay, see, it's like saying to the system, like, okay, you take care of that and you are like optimizing towards this. So you will get that. And you kind of trust that the system is going to its inner kind of state is going to be able to get those alignments. So for sequence to sequence models, what you have is normally you have an encoder and a decoder. So an encoder, what you do is like translate like these features that you have, which is like from the audio signal, translate those features to another, like a higher dimensional space. It's like imagine like translating those features to a language more richer for the system. It's like the system, like the encoder knows its let's say language, creates a like internal language, and it transform that data to a way which is more easy for the system to learn from. So then you have those encoded features, and then you use a decoder to decode that data, and then you create like what is called like the transcripts, or there is different ways like phonemes or words or subword units. You will see that. I will explain that later. So then you can also use these language models. For instance, now with the SpeechBrain, it will be easy to fuse or to add this massive language model like GPT-2 or GPT-3 easily, which wasn't the case for previous ASR systems. So that's why I would say that we are through a breakthrough in ASR, like since last year and maybe this year as well. So these are four libraries that you can see there in the top left. There is SpeechBrain, Fersec, ESPNet, and Caldi. There is links there, so you can go like and check them out. So a standard ASR pipeline for sequence to sequence models is like you at the beginning have like imagine like this speech, like of this person talking, or someone talking. So then you embed that speech in some features with from X1 to Xn. And what you do, that this is a shared encoder and attention decoder. So what you do is like you map that information, input information in a higher dimensional space, and then you use that to decode and produce some output. In this case, what we want with this output is like, it's called subword units. So then it's a way a way, because if you imagine that you have the network and then you have the output of the network, if you assign one class for each word, you can have easily 200,000 classes, which is very high, and will be very, very hard for the system to learn from that. So what they do is that they embed all that information in splitting the words and things like that. You can go deep, like delve deeper in this kind of approach, but also you can, for example, output phonemes or letters. That's also possible. So it might be a little bit like kind of tricky to follow up this, because there are many letters, numbers, and whatever. So this is a easy way to see how it works, this sequence to sequence model. So you have this encoder, then you have a feature vector, which is the higher dimensional vector. Then you pass that to the decoder, and then you get an output. And that output normally is, well, these software units of what your task really demands or needs. So this is more, let's review more or less like specific parts of using a speech brain for ASR in this case. So as I mentioned, like at the beginning of the tutorial, we have like this class that is called encoder decoder ASR, which is an interface, easy interface to embed all those systems in one class, and then you can get, there are some functions, for example, for transcribing and things like that. So from that model also you can get the tokenizer, which is this I think is highly used in NLP, and also is getting some popularity in ASR. So basically, like, let's say that you have this phrase, this is the Mexican NLP Summer School, thank you for attending it. So then you want to know how the system, what is going to be the embedding that the system is using for training. So then you can, for example, encode that, and this is how the system is kind of representing it. And also you have like the IDs or things like that. Some, those are more detailed, more fine like granular details that you can also go later or go there. So also for doing ASR with pre-trained models is more or less what we presented before. So you just need to get your model, initialize the model with pre-trained models. And I put this this is the way that how you do it if you get the models from the GitHub repository that we share. So basically you can do like this very straightforward, like that way. So then you load the audio. So the audio, what you do is that you pass from this like BAF file, flag, or whatever encoding way that the audio is, and then you pass it to Python, and you convert that into a tensor, which is like how is interface. And then you can just apply this function, which is transcribe file, and then you get the transcript. So it's important to know, like, maybe in NLP and this other kind of task are also fields in machine learning. There are different like metrics for knowing how accurate is your system, but for ASR there is a specific way to know how accurate is the system. It's called word error rate. So normally what you are is measuring the number of substitution, deletion, and insertions that your ASR system is kind of creating. So let's say that you say this specific sentence, and then one word is deleted, or it can be substituted or deleted. So that way you can know how good is performing your system. So also depending on that, you have different like kind of metrics, like character error rate, sentence error rate, and phoneme error rate. So basically, just a better explanation of how this works. Like a substitution could be like, for example, if you have rain, then if you change one letter of this is like a substitution. An insertion would be like adding one. In this case, is not words but letters. So an insertion would be like to add in a new letter into the word, and deletion would be to delete it. So this is more or less how you measure the system, and how at the end it's the goal of the system, like to reduce this error. So yeah, I don't know, should we go with a break?
Yeah, I think we could do like a 10 minutes break. That's fine for you all.
Yeah, I hope it's fine for everyone.
I didn't see any
yes, guys, so we can come back at it's sorry, let me check my clock.
I don't know, like 10 minutes or 5 minutes, I don't know what's
okay. 15 minutes before 8 p.m. here, right? So we take we
Okay,
take a
10
break of
minutes.
15
Okay.
minutes, 15 minutes, everyone. So if you have any questions, you can put it here.
Yeah.
So
Yeah, guys, if you have any question, or it would be really nice if you can just put it there. Don't be afraid. Just leave it there, and there we'll try to take.
there was one question about the slides, I think.
Yep.
In the slides are in the repository, the Git repository also.
Yes, there's a link to the slides in the Git.
Yeah,
Okay.
it should be there in the GitHub repository.
Okay.
So yeah.
Okay, thank you. So see you in 15 minutes. Thank you.
Yeah.
You can go for one coffee, some water.
Yeah, I did one.
Great. Thank you.
Okay,
See
thanks.
you.
See you then.
Okay, so let me stop sharing the screen. Okay, thank you guys.
Okay, now I can share it. Okay, good. Okay, so yeah, I just want to. So we were here, right? Yeah, just there. Okay, so 1 second. So yeah, so we were talking before about the ASR kind of techniques or methods that we have at hand to perform well ASR. So, but one of the main things that we were discussing is that like supervised data sometimes is very costly. Like I put the example of my project where I am working on in air traffic control. It's super expensive to produce the data. Sometimes it's very noisy. It's very like hard to get, well, label it or yeah, something like that. So, but there are some like new things that come into the rescue to help us with this, which is called semi-supervised training. So for ASR specifically, I want to first put this slide that Jan LeCun put. I don't know if you're Jan LeCun, but he's well recognized in the area of artificial intelligence and so far. And he did this, he made this slide in 2015, and he was mentioning that like there are different ways to try a system. So we have like on one side we have a pure reinforcement learning where where we are just giving like a feedback to a system, like a very small feedback based on a lot of data that we need to process before. So normally it's like a few bits for some samples. So let's say that yeah, in reinforcement learning for supervised learning, what we do is that we label this data and we say that this data is like a, let's say that this audio signal is this specific word sequence and just that. But for on the other hand, we have unsupervised training and like a self-supervised training. What we do is that we let the system learns like a, maybe sounds not correct, but kind of whatever it wants or whatever he or she or it thinks it should learn. So that what is do is like you put this audio data, you don't give any samples, like any label, sorry, and then the system trains for some time, and then it learns like a good representation of a speech. And it has been like shown like in the last two maybe 1.5 years that this kind of training it's super useful if we want to apply this in different like downstream tasks. So basically it's kind of a GPT-3 or this huge language model that you train the language model and then you kind of fine-tune the model for different like a task or thing. So imagine like each language is a task or each things like that. So what you do is like you put to the system a lot of training data for it could be from several languages, and then you let the system learn whatever he wants to learn. And sometimes, like most of the time, it like at the state of the art of the best system are trained this way. So like at the moment. So, for example, for instance, if you want to improve more the ASR system, what you do is like you leverage this non-transcribed data for improve the system. For example, in my task that is air traffic control data, I am using that like data from different airports, which has different accents from different air traffic controllers. Normally, they need to speak in English. So this different data helps the system to kind of learn like a representation of how the speech in a traffic environment works, or how it's like normally how people speak. So that's a good way to leverage this non-transcribed data. So this is, for example, something that was just from Facebook that is called self-supervised learning, and it's called the model or the system is called Back-to-Back 2.0, which is a system that is just using 10 minutes of labeled data in English, and it's like achieving really good performances. So normally, as I mentioned before, the metric for ASR system is word error rates. So in this case, like is when you have like word error rates less than 10%, that means that 1 out of above 10 words it could be misclassified. So having a error rate less than 10%, it's fairly good. And the system is achieving that with just 10 minutes of label data, which is like a really blown mind. So that's something that you might want in the future to start like checking and things like that. Okay, sorry. So as you might know, might not know, maybe Facebook is not just a social network. So they have a lot of there has been a lot going on in speech recognition from the FAIR team, which is Facebook AI research. So now they are talking about unsupervised learning, which is like doing ASR without any label data. So what they do is like they create this system that's like maybe less than 1.5 months old. They release this. This is everything online in GitHub. So you can just go and start using the models and things like that, which is very interesting. So how it works is like basically you have the ASR system and you use these systems called GANs, which is generative adversarial networks. And then one part of this system is the discriminator, which normally could be a language model. So then and the generator is the ASR system. So you tell the system to start generating like a word sequence. In this case, the discriminator say, okay, the sequence doesn't make sense, so this is a fake. And then after some time, after you give more training data and the system start to converge, start generating like a good representation or meaningful word sequences, like for example, how are you? And you are doing this in an unsupervised way. That means that you are not telling the system, okay, this let's say this recording it's having the features that means how are you. It's not like you are not giving that. It's totally unsupervised. So that's kind of a breakthrough in my area, at least in ASR. Of course, there have been some like a modification and picky things that they do to make this work, but still is like a good way to for example provide people with ASR system, for example, for Swahili. So this back-to-back, they call it back-to-back U, and it's producing ASR completely without any supervision. And then it's like this is the native speaker transcript, and it just produces like a very small errors and things like that. And I think that this is a very breakthrough in our area. So a bit in depth of semi-supervised learning in ASR, what you do is like you have like a few annotated data, and then you have like a large amount of non-transcribed data. What you do is that you first train a system. This is like the old-fashioned semi-supervised learning. So you train a system, and this system, then you use this system to transcribe or get the text of these these audio files, and then you combine that data with the supervised, and then you have the unsupervised, and then you have the semi-supervised data, and you retrain the system. Sometimes they do it like iteratively, and that have shown that it improve the systems, so that you can leverage when you don't have like this kind of annotated data. So here in this slide, you can go later and start checking like different directions in ASR, like very state of the art, like from this year and maybe later last year. And it's like the best way you can kind of get up to date of what people or researchers are doing in this area. Yeah. No, Mael, if you want to go with
I think that now is the moment we'll jump on to actually making the app and the demo that has been announced. Just a few considerations initially. As you've seen now, we have the whole world of NLP that's now being open, because you have systems that could make less than 10% errors. So just bear in mind that the ASR transcript will convey errors, especially on names and on some rare words. That's quite common still. So if you want to do name entity recognition on top of ASR systems, I'm not saying it's not the most trivial if you want something to work in the best, like in realistic scenario in a sense. So there's some methods that are being developed to boost some phrases or words in specific context. I'm happy to point you towards to some papers if that's something you're interested in. And I think Juan Pablo has been working on these topics also. and your language model, in a sense, will play a big role. And having in-domain data to fine-tune your language model can help a significant margin. If you're interested in criminal applications, just consider having a language model where you can collect this kind of data. That would be much useful. Okay, so Juan, I don't know if you can, or I don't know if there's any questions that we can take.
Is there any question? Okay, sorry. Maybe I will stop sharing and then. Is there any question?
Someone from the attendees has
wants to speak.
I think has a question, but
yeah. In language model, is it possible? In language model, is it possible to continue the pre-training or post-training to incorporate more information, for example, domain adaptation, without restarting the pre-training from scratch? Is that possible and used also in the acoustic models, for example, to incorporate a new accent for which now we have data? If yes, can be done with the speech brain framework? Yeah, I can take that at least for the side of acoustic. Yeah, for the acoustic model, that's what we do normally. For example, in my project that is ASR in air traffic environments, it's very different how people talk depending on the country. So you can imagine that an air traffic controller from I don't know, Belgium or Germany or Switzerland, it varies a lot. So what we do normally is like we train a system with all the data, like massive, like a lot of data, and then you do some domain adaptation. So you can do domain adaptation of everywhere, like of everything. Sorry, like acoustic model, also the language model. So you have a big language model, and depending on that, then the system should improve in normal cases. And regarding the speech brain framework, yeah, of course, like what we are doing now is we just get those pre-trained models to do inference or to do speech recognition, but then you can start from there. And it's much better to do that because you are like leveraging all the previous like training and things like that.
And for example, one of the common models now in ASR, as Juan Pablo mentioned, was WEF2VEC2. And there's the WEF2VEC2 XLSR 53, which is actually like a pre-trained WEF2VEC2 on 53 languages. And it's using like many open sets, open data sets. You have thousands of hours of training data that went in there. And because it was made to learn meaningful representations of speech in 53 languages, that's why you can fine-tune it for like some languages really well. And if you start from that, then in a sense, you can take this pre-trained model and then just fine-tune it on any language that you like, even models that were not part of those 53 languages.
Exactly, because it's like you somehow are getting some, like your system is getting like more or less like the representation of how people talk, even if we know that different languages have different phonemes, different grammar and things like that, but still you can recover something from there. At least, for example, the alignment problem, you don't know when a start, when a word is starting or ending. So these pre-trained models are like really kind of intelligent in aligning that, and from that is like already something given for you, like already something done. Yeah. So there is I don't know, Maya, do you want to add something for?
Oh, please, that's all good.
Okay, there is another question that says, can you give us a little, from Juan Flores, can you give us a little of intuition on how it's possible to predict the true label of the audio without annotated data? In other words, how does the GAN can perform that? Well, as far as I haven't gone like through the whole paper of this new WEF2VEC-U, but what it's doing is like the GAN is just evaluating how meaningful is the phrase that the ASR system is producing. So imagine that you put an audio file and at the beginning it just start producing like a non-meaningful words or whatever. But then at some point, so the discriminator, which could be, I imagine that should be a language model. What it do is that it tells, okay, this is fake, this is not real, this could not be a transcript or a meaningful sequence of words. So what you do is like the system start learning from that, and at some point the system is going to to somehow to make like a good sequence of words, and from there the model start learning. And like you, of course, you need a lot of data and a lot of GPUs and like a massive computer resources to achieve these kind of things.
Okay,
There is one question from YouTube. If you have the time to answer.
Yeah.
It says, will ASR play a significant role to learn or understand the language of the whale, ants, and bees?
To understand the language of the animals in general. You mean like animals? Yeah. Well, actually, I think there is a couple of PhD students in our research lab that are working on. I don't know if like exactly like transcribing or saying what a dog or cow is saying or something like that, but try to understand a little bit how these sounds are produced. But I don't know. Maybe
I don't know about ASR for animals. But
yeah, it's most related to understand the communication process. I think probably that's the question, right? Like it's not.
Yeah, there's a high chance that you can identify patterns in a sense, and that based on those patterns that you analyze, then you can derive, okay, from prior experience, it might be that they do that in such situation.
Yeah, exactly.
Then they do that again. But it's more like you can tackle it as a pattern matching thing.
Yeah, that's a different direction, I think, from.
Yeah. But I'm also aware of applications of X vectors in the speaker verification task being applied to animal spotting. For example, you put a microphone in the rainforest and you would like to spot a specific bird, and so you just train the speaker verification model, so like a bird verification model, on a large amount of data collected on these types of birds. So you just need a large database initially of all the sounds that these birds make and the identity of that bird. And then you do the enrollment of that new bird, and you can then verify each and every time this bird has been spotted there again. I've seen actually like a few startups doing that, which is also like a cool application, and you can really take this same type of technology. I'm not saying that the X vector is probably like the way you would have intuitively gone for this type of task, but it just happens to also work well, and I think it's currently state of the art also in this domain.
Interesting topic. Yeah.
Okay, I think that's all the questions. Yeah, thank you guys.
Okay, cool. So Juan, if that's fine, we just jump to the to making the app, and then we have some time to go through the notebooks. That's something we can do. You're muted.
Yeah, sure, makes sense. Yeah, you can go with the app, and then I go with the notebooks.
Yeah. Okay, cool. Okay, now the fun part. Building a voice assistant. Well, very basic. I have to lower down the expectations, but it will still be cool. The point is, we'll build a voice assistant that will recognize your voice and block the query if it's not you who's speaking. Recognize the speech that's being said, so that's ASR. Display the transcript on an app. I'll also introduce you to like a small framework that I use for a web application. That's always a very cool demo to make in a sense. Then we will identify the query, the topic of the query. And if the topic is weather forecast, we will move forward to the next step, which is identify the named entities, and especially the geographical entities that are being mentioned. So you see where I'm going. If I spot that the intent of the person is to get information on the weather in some place, then I will query an API, and I will say, what is the current weather in this place? You can go further. You can also, try to find named entities also related to, dates. So maybe you want next week, and then you can phrase your query this way. We'll stay very simple. And then you want to display the output on the app. So the way it will basically work is we'll make this app where you can give a command, then we'll grant the access with a specific score, we'll produce the output, then it will say, are you like more interested in weather forecast or calendar and meeting, you can think of any application. Then, I mean, that's just up to you to build something cool there. Then it detects, okay, we ask for weather demand, and then we extract the named entity and we display what's the weather like in New York right now. We'll use Streamlit. I don't know if you guys are familiar with the Streamlit. It's just a easy framework built on top of, I think it's built on top of Flask, just to create easy, web interfaces in a few lines of code. It has a predefined template. It can take any user input. So the user can input speech, can click on buttons, can input images, and then you can apply any kind of processing that you want. So that's also being used for machine learning applications to show the inference of a model, but also for a dashboard that you want to do for some specific projects. I invite you also to check out the tool. We'll stay at a pretty high level thing. And that's the moment I'm leaving the slides and we're moving on to this. So basically we have this GitHub repo. I don't know, Juan, maybe if you can copy paste the link in the chat.
Yeah, we'll do.
You had it initially done. So in the link of the chat, that's also where you'll find the link to the slides directly there. So the point is that we'll make an app that you can pretty easily install, run the app, and have the whole thing. So the way it's organized, so you don't need to worry about the notebooks, the pictures, the pre-trained models, all of that is my local files only. So what you see is I have an app there, app.py. I have a temp folder where you can guess that it's where I'm storing the queries of the user and what I'm using for ASR stuff also. So I'm recording the thing in live, and then when I stop the recording, somehow I'm removing the temp once it's being processed. So if I just go in the app, in a sense, you'll see that we import many things from the speaker verification module, ASR module, NLP, voice activity detection, and weather forecast modules. All of that are just modules that have been developed for this. So what you see here is that with a Streamlit, you just do import Streamlit as ST. And if you want to create several pages in Streamlit, then you just have a select box on the side, and you use st.sidebar.select box. That will just allow you to have a roll down menu, and the way that would be displayed typically is like this. So that just allows me to have 2 pages, and then if I say, okay, the person clicked on enroll speaker, so I'm showing this. So I'm showing this first page, and then otherwise, if the person clicked on voice assistant, then I'm showing this second page. So just to have a layout architecture in a sense. Then I just preload my models. I'll just show you the functions afterwards. And then let's dive in the page of enroll speaker. The reason why we're having a page dedicated to speaker enrollment is just that we, in a sense, want to be able to say whether it's the correct speaker that's making the query or not. So if you want to add a title in Streamlit, you can just do st.header. That will just give your page this information. Then you can say start recording. So you can that's a button I'm triggering. So if the person clicks on start recording for 4 seconds, here I'm taking the easy case where I'm making a recording for a fixed length. So if the person clicks on, let's go to the enrollment page. So that's, I have my header, I have my button that says start recording. So you can see that, adding button, usually if you had to do it through another framework would be, not saying a pain, but just takes a bit more lines of code. Here I just say if st.button, and then I say the thing, then that happens. The way you would do the recording is with a library named sound device. So that just allows you to do a library of a length of so I have a sample rate of 16,000. I just have my sample rate of 16 kilohertz. I have a length of 4 seconds, so I'm just like 4 times the sample rate. I have only the recording being made on one channel, and I am waiting until the whole recording is done. When this is done, I'm removing any temp file that I saved, and I'm writing that file there. Then I have 2 things. First, I want to focus only on voice activity detection. So on the part where I have speech actually in what has been spoken. So I first run the voice activity detection, and then what I want is extract the embedding. So that's my enrollment. So from the sense, when I import the model, you remember on that picture I had where I had the large speaker identification databases. That's the pre-trained model I imported. And then I'm extracting the embedding for the enrollment data. And then I will extract the embedding for my test data and see if they match. And then that just grants the access to the rest of the app. So that's what I'm doing here. I'm creating the speaker model. So by creating the speaker model, what I just mean is that I'm saving the embedding in a pre-made, in a pre-extracted manner, because every time the speaker is coming again, I won't extract every time the embedding, but I would rather extract it only once and then compare this trained embedding with this pre-extracted embedding with the rest of the embeddings that I will have to compare with. I'm using Pickle for that. And once you have that, the enrollment is said to be complete. So we can do that like live, see how that works. So after just a few seconds, what I will do, I don't have to talk about like a specific topic. So here it's making the recording. So I just have to speak for 4 seconds straight. The enrollment is complete. What happened then is just that my data has been saved in the temp here. So that's the file that was saved a few seconds ago. So that's cool. Now if we move on to the next one, so the enrollment is complete. First, I will need, in the logic of what we're building, I will need to compare the file, the enrollment file with the test file, and then I will need to do the ASR and then the bunch of NLP applications. So I'm loading the speaker model again. Then I'm taking the user input command. So what's the weather like in New York, for example? So that's something I can already launch. It just takes a few seconds to run because we're on CPUs there. Okay, so let's go like this. Just need to wait. What's the weather like in New York? Okay, so the access was granted with a score of 50%. So I have 50% cosine similarity between the 2 recordings. It's by far not a perfect model. I'm also like a non-native speaker, but this is the type of work then you can fine tune on later. So now it's running. So now what it's going to do is so I'm just saving that command and I'm running my speaker verification model with the command.wav. So what my command that I just gave versus my speaker model. And I'm just trying to see whether the query gets accepted. So here the access got granted. So that's cool. And now if the access got granted, what I will do is I say access granted with a score of X%. And then I'm producing the transcript. So that's, we'll jump into these files right after. I'm just producing the transcript. I'm running topic detection. I just show you, I picked a 0-shot topic detection pipeline where you can either talk about weather forecast or calendar meeting. And since it's a 0-shot classification, it's just the way it works is like a template matching in a sense, where it's looking at which is the closest template to, in terms of like embedding similarity between the query, like what is the query of a user, and the sentence, this question is about weather forecast, or this question is about calendar meetings. Okay, so that's the part where you start to do NLP. If the topic is weather forecast, then you have this success of, okay, it's a weather forecast demand. Then you need to get your city. So that's where we apply named entity recognition on top of the transcripts. And once you have your city, you get your current temperature and weather description with our function find temperature. And if the weather forecast is not, if the weather description is not known, then what you just do is the temperature is X degrees with, and then the description of the weather. So that's typically what has been done there. The weather demand has been detected. So the topic, then the weather demand has been detected. Spotted New York as a named entity, and the temperature right now in New York is 20.4 degrees. So that's the framework. As you can see in Streamlit, that's still fairly easy. If you want to display something, you do st.write. That just displays the some text somewhere. If you want to put it in the sidebar, you do st.sidebar. If you want to have a green message for success, then you just do st.success. It's very easy to get used to it. And as you can see, in like 95 lines of code, minus the spaces that I jumped, that I skipped. But you just get an app that does this. Now, the fun part is what's in these different files. So we'll start with the speaker verification. So my pre-trained model is just my encoder classifier. So that's the eKappa TDNN architecture from SpeechBrain. Then I have another function that is compare embeddings. So that's how do I compare the extracted embedding from my speaker model with the embedding that I just extracted from my test data. I have one function to get the actual embedding. So that's just encoding the batch using the pre-trained, using the function from SpeechBrain. And then I have the option to run, I have the function to run the speaker verification. So what it's doing is it takes as an input a path, a speaker model, and the verification model plus a threshold. What it's doing there is it's the path is the path to your command that you just spoke. You will get the embedding for that. And then you have the score. The score is just the comparison of the two embeddings. And then you return the score and the decision. So that's what we're doing in the speaker verification part. Fairly easy, 30 lines of code and you're there. Now, if I move on to ASR, it's even faster because they just have the loading of the model that's done there. And if you remember, in the app, that's where we had the inference that was being made, the transcribe file function. And here, for example, you can take this model, you can specify a source, and then you can specify like a saved directory. You can load any pre-trained model that you would like. There's tons of them now available on SpeechBrain also. There's more than 20 of them available on the Hugging Face repo, also of SpeechBrain, and they have a lot more in their GitHub repo. Okay, now we're interested in the NLP application. So for the NLP, what I'm just doing is that I just need, I'm using Spacey basically to do the named entity recognition. And I'm also using the zero-shot classification pipeline from Hugging Face to do the topic modeling. So as I told you, the topic modeling is fairly easy. What just happens is I have my query embedding. Okay, so that's my query embedding. And what I want to do is just compare it with the a hypothesis template. So this question is about, or this conversation is about, or you can think of any query templates that you want. And what it will do is just compute the distance of the embedding versus the sentence, the embedding of the sentence, this conversation is about, and then weather forecast, or the other one that was meetings and agenda. So the other one will be this conversation is about, and then I'm putting M, meeting and agenda. And we'll just compare the embeddings from this and from this, and we'll say, is it closer to one or to the other? And if it's closer to this, then it's a weather forecast demand, and that's the thing I'm going for. So that's just this pipeline that I'm using. So for the detection of the topic, I just have this classifier after loading the model. One thing that I have to say about Streamlit also is that you can put stuffs in cache in a very smooth manner. So you just add the decorator at st.cache, and it just puts your model in cache, and it just avoids to reload the model every time you need it. And if you put like the output also of a function in cache, every time you just redo the computation that you already did previously, so you just need to recompute something on the same data again and again for debug purposes, it will store also that information. So that's a pretty cool feature if you don't want to get your hands dirty on how to do caching on this type of stuffs. And here what I'm just doing is displaying the graph of, that's these 2 bars there. So that's done with a Plotly Express. And if I want to display something from Plotly, I just do st, so for streamlit.plotly chart, and then I can pass any function here. You can also pass matplotlib graphs. It's just up to you. I like to use Plotly Express for this. And then you have the identified topic. This just comes in a dictionary for the output, but I'm just taking the identified topic there. So this is for this. Now for the named entity recognition, while I'm not teaching you anything there, we're using Spacey pre-trained model in English. You need the English Core Web SM corpus pre-trained model, and for each of the entities, if the label is I think GP stands for geographical something entity. Yeah, so that's just the class that we're interested in. If you were interested, in person, then you would just go for I think that would be PR or PRS. I don't know. But yeah, so we're interested in entities, and I want the text of the entity there. Okay, so that's for our NLP applications. And now we have 2 things left. The first one is the VAD. I won't dive into this. It's how to do voice activity detection in Python. It's an energy-based voice activation. Basically, the energy will look at the amplitude in some of the energy in some of the segments and try to classify whether it's a speech segment or non-speech segment. And so that's the one I'm using, if you remember, right before doing the speaker embedding extraction. And finally, we have the weather API. So for the weather API, I'm using a open weather map. And I'm just making a query to the API of open weather map. Fairly easy. I'm just reading, I need a key there. So you can just go on open weather map. Okay, and then you would go in your thing, and then you can ask for API keys. So that's the kind of keys you'll see. I'll reset it afterwards. You just copy paste that into your key.txt, and then you have the find temperature function. So the point is not to go in this. Just gives you the output in kelvins, so you need to convert it to Celsius degrees. And if ever the output is not 404, so page not found, then you just return what's the weather, and so you just want the current temperature and the weather description, and you can also get pressure, humidity, any kind of application you're interested in afterwards. That's something you can do, and that's about that easy in a sense. It's it's not much work when you put all of this together, just because we leverage many pre-trained stuffs. Of course, it's up to you to dive into really cool applications. But if you want to automate some tasks, for example, that's something you can directly do there. And what we've made there just gives you a template here. It just gives you a template to do so. Plus, I think Streamlit is also a good tool to remember for showcasing some of your work later on in the portfolio, whatever. So yeah, I don't know if there's, I think that I saw some questions in the chat, but I can't click on them. Oh yeah. Okay, yeah, I don't know if there's questions.
Hi, Mal, thank you. There is one question from YouTube. I think this is before you started the description of the application, but probably you can take it now. It's what do you think about endangered language that usually don't have any training corpus? Can this be benefit from Wave to Back from Facebook? I mean,
yeah, I mean, it's as long as, I mean, we talk about low resource languages when you don't have thousands of hours of training data. For example, I was focusing on training some ASR systems in Hebrew, and for Hebrew, it just turns out that the biggest, data sets that we found that were available for academic purposes were only 5, 6, 7 hours of training data. It's still a significant effort to build those data sets. And if you start from 0, I'd be curious to see how like a WAV2VEC would work, but I'm guessing it will come with like many limitations still, because there's no magic model in a sense. So I think a few hours of training data is still highly relevant and highly useful, especially if the model is not seen in the training data of an XLSR 53 system, for example. If it's highly different from any, if it's just a language that has not been captured in those 53 languages, and that's quite far from what we know in Europe or in South America. In that case, they might just end up being a bit harder to get proper results.
Yeah, thank you. I don't see any other questions, but I'm not sure if people were able to try this. We put all the instructions in the Slack.
Yeah, very well explained.
And well, also Juan shared here. I hope everyone is able to see. I think it's a good, something to start working on, right? I mean, this what you share now. I have one question, Mile. You show at some point to do this speaker verification, you use cosine similarity.
Yeah.
Cosine similarity is also very frequent in when you are working with text only.
Yeah.
And my question is, for example, is this like the normal way to do it, or there are additional metrics to detect similarity? I mean, the idea of the cosine is very intuitive. I get that, but I wonder if there is any other way to do this.
Yeah, so cosine similarity is just shown to work empirically quite well for some ResNet architectures, but for the rest of all speaker verification models, usually we do a probabilistic linear discriminant analysis backend, so PLDA backend. And so you would have to train a PLDA on target data, like on the development set. And once you have that, it's just one good way to like reduce the dimension of the vector and perform the classification. And it just, so that's usually the way to go. And SpeechBrain has an implementation of PLDA, which is also cool, that I've been playing around with. So that's also something that you can totally do if you have some development data. And what I mean by development data is just there would just be some data that you have collected that is annotated in the sense that you just need to know who's speaking in the recording. If you have a few hours of or dozens of hours of these kind of data, that's cool. And just needs to be in the same domain than the data you're interested in. So that would just mean if you're interested in telephone conversations, you just need to have this telephone conversation environment also, and maybe not take data from YouTube or from the TV broadcast news, for example.
And Maybe another question I have is regarding the sampling rate that you showed. This is fixed because the configuration of this example, or how do these parameters affect the performance of this app?
They do affect quite a bit, whether it's for ASR or for speaker verification. What you usually find is, here I'm storing them at 16 kilohertz for the simple reason that the model was trained on 16 kilohertz data from YouTube. But if you train the model on telephonic speech, then that would be 8 kilohertz. Usually that's the sampling rate from telephone speech. Either once you have your new data, you cannot pass 16 kilohertz data to a 8 kilohertz trained model. You need to do upsampling or downsampling of your data, and that usually is quite a bottleneck for the performance of your model if you do not record the data, because upsampling of the data, basically you just have half of the data that are missing, and then you're just creating these various methods to do that, but you're just creating twice as much data than you initially had. And so you can think that it's, of course, there's less information being captured there, and the models don't work equally well if you upsample the data.
For what I know, this is like it's very normal not to have this type of quality on the data. I mean, because also it's not, how to say this, having high quality data is also expensive in the sense of storage, right?
Yeah, definitely. Yep. And it's the whole problem in the end is just about we still get to this training data problem, because sometimes, okay, you have the right quality of data or you have the right amount of data, but then you also need to have the right domain data, and sometimes you're more interested in far field speech recognition. So like, those voice assistants, sometimes there's people speaking from the other end of their living room. So you're more interested in having training data that are recorded from someone speaking 5 meters away from the microphone. Sometimes you need your language model that is fine-tuned on some criminal data or for some other types of applications. So this question of the training data and of the having a mismatch between the potential pre-trained model and your actual application often comes back. And so that's why it will be hard to say I'm building my startup out of this, out of an example or out of a pre-trained model that you would take here, because it's just highly likely that whatever application you're going for, if you want like to make a medical chatbot or whatever, then the language model would somehow have to be changed. So you would need to collect data. There would be text data, but we need still to collect data and fine tune that for this. And sometimes the patient is talking from pretty far, so you also need to have relevant training data for that. So there's, in a sense, always, what's really cool now is that all of these models are accessible, and it just allows you to do the benchmark. And those libraries will also allow you to do the fine tuning of the data, but there's the question of the training data that always comes down.
Maybe let me check if there's any question. I think no. So
is there any?
Probably.
Yeah,
I don't know if the people is trying to have tried to run this or not. Maybe you can tell us. So if you find some issue right now,
or you put some issue there, you can just.
Yeah, I'd be curious to see if like any applications comes out of this stuff. Like, I'm not saying this is a good baseline to do like stuff on top, but if you somehow fork this and go to build your own chatbot, and especially what you do with you can consider just the speaker verification and the ASR as black boxes and use them as such. Maybe replace them with the model in the language that you want, or but then also see the kind of NLP applications that you would do, because I'm more of an NLP practitioner rather than an experienced user there. So it would be still cool to see if you guys do something with that.
Yeah, I think it's like a good starting point to close the loop, like, to adding this ASR part, like into the pipeline. So yeah, there is also maybe in the tutorial GitHub repository, there is a couple of Jupyter notebooks that you might like to check, guys. So it's all up to you to go there.
That's just basically that's recipes and notebooks to train your own models or play around with pre-trained models. Specifically the for the ASR, you can go more in depth with this. I think Juan Pablo made a pretty good work. We unfortunately won't have much time to dive into this.
Someone in the chat is mentioning that he ran out of RAM memory.
Yeah.
What are the characteristics of your computer, Mael and Juan? So maybe people can have an idea.
Yeah, I bought a 32 gigabytes RAM computer just to avoid that.
What you can do is that you can maybe import the notebook to Google Colab, and with the GPU that would be much easier. You won't have, and it was super cool, super fast as well.
Yeah. Other option is also you can process the data, so you can avoid the st.cache functions that I put. It just puts the stuff in your cache. If you remove that, I've just found by partitioning it that it's helping the whole thing, because the cache management sometimes is just assuming that you have unlimited RAM. And otherwise you can process the data by chunks also. So if you want to do the decoding of for ASR of a WAV file of 5 minutes at once, my computer will crash, basically saying it was not made for this. Like speech is still made to run on pretty big machines.
Yeah.
So you can try to do like the decoding on frames of 10 seconds, for example, and then just concatenate them all the way. It's not the best, but it's just it also works.
First solution to this kind of problems.
Yeah. And any application, like any serious application that you build on top of that, you would probably at some point deploy it on AWS Lambda architecture or like Google Function architecture, where whenever there's an event of a new speech that's being uploaded, then you just have the GPU resources to run that. And one of the really cool things, I guess you guys know about also, is from Hugging Face, that if you want to leverage any GPU that you have for the model directly, you just add 2 CUDA, and that would just leverage, find any GPU and handle this this GPU computation for you. So that's basically like 2 words, and you can also move that to GPUs you have installed or on your instances.
Yep.
There is one question from Juan Flores. Do you see it?
Let me check.
The VAD function in the VAD.py file is used to recognize the speaker. I do not recall what it was supposed to do. So VAD stands for voice activity detection. So it's just detecting the segments in which someone is speaking, so that if in the middle of the enrollment data there's a blank, then you just remove that blank, because otherwise that would be captured in the embedding that you create for your speaker. And that's something you want to avoid, because it might be background noises like kids speaking, or if you need coffee or whatever.
Just silence most of the time as well. So
that's what you want to remove.
Enroll. Just for the sake of sharing a story. Some information with us.
Okay, yes, that was a comment from Celine.
Yes, I didn't see that. Yeah.
So if I just read it out loud, just for the sake of sharing a story, I'm working on a social robot who is intended to bond with people. For this, the robot should extract some information about the person, so it can remember it and discuss about, say, the person's interests. Our problem has been that ASR plus information extraction usually fails, since even one wrong word on the ASR side makes the whole pipeline fail. I'm trying to train an end-to-end model that to extract triples as in the knowledge, as in the knowledge graph from speech. Had spent many months figuring out the speech tech on my side. It's not my expertise or my supervisors. This tutorial is super useful for me. Yeah, so thanks a lot for, I mean, that's a very cool application.
Nice.
I think you are touching upon the personalization of like speech interaction. That's also really cool. And indeed, as you mentioned, for some stuffs, missing only one word in the ASR pipeline is makes the whole thing very tricky, because for many NLP applications, or even sometimes punctuation or capital letters are not the stuff that are best transcribed with ASR systems. And sometimes it just happens to be very important for some pipelines.
I feel like something that you might like. It might be nice to try is that sometimes ASR fails. When those words fails, is like fails maybe the pronunciation or something like that. So it might be maybe nice to if you can cluster like words that are similar to pronounce or with similar phonemes or things like that, and then you can somehow leverage that. Like.
Yeah. But if you want to open source it and you want to paste the link in the chat, that's also something you can do, and it would be cool to see if some people decide to work on this.
Yes.
And if you have enough data per speaker, you might also want to, just don't know how many interactions you have recorded, but you can also do some adaptations of the language model on top. It usually requires like lots and lots of data, so I'm guessing you're not there yet. Cool. So you should just share the link.
Okay. Yeah, the paper robot.
Yeah.
I don't know, Selene, if you want, I can open your microphone. So if you want to, just let me know. Yeah.
That looks like an interesting.
Just give me 1 second, because I think you are able to turn on your microphone, Selene.
Yeah.
Hello?
Hello.
Hi. Yeah, thank you for the tutorial. It's made like everything much easier. I was very frustrated and about to give up on this project, so this gives me energy. And yeah, I had two big problems, like trying to figure out the whole ASR and this voice activity detection. I didn't even know the terms, and getting training data, because that's an also big problem. And another thing that I really like with this is that the app also gets visualizations. And because I've worked with knowledge graphs, then that is very visual. So I can show directly to people, you said this and it translates into this graph. And we show people what we know about them, which is really important now with explainability and privacy and all these things as well.
Yeah, definitely. And to share a story also on that, part of the work that I'm doing in my PhD is also related to knowledge graph representation of the information captured in speech communications. So there's not only the identities of two speakers that will just build two nodes that are linked by an edge, but there's also the edge itself has content that is the ASR transcript, but people would typically mention other people in their conversation. So if I'm, for example, talking to Esau, but I'm mentioning Juan Pablo, it also means that I know Juan Pablo and that Esau knows Juan Pablo. And then I have this representation that, it's just expanding on and on. And this whole thing of also building trust and having a transparent solution, I just found that through Streamlit, for example, it's just a very easy way to display what has been captured in a sense. And when I'm working with investigators, I just happen to see that they want to know the output of each of the files that is being processed, rather than having the black box output. And see what kind of named entities are being captured or whatsoever. So I can totally relate to your challenges.
Yeah, maybe I'll reach out over email later, because that sounds really overlapping indeed.
Sure,
and another fun fact is people talk differently to robots than they talk to people.
Oh yeah.
So that also changes things a little bit. And I was wondering if it's worth gathering recordings and maybe retraining an
Yeah.
ASR model for talking to robots.
Selene, I don't know, by the way, but I don't know if you are aware, but in IDIAP, where we work, Institute, they also work with the paper in something similar, like a setting up the robot for a shopping center. So it was like they were like checking how to, how to detect how many people and what were around the robot and which one was talking. So it was like getting the direction of, it's called like direction of arrival of the of the speech, and then they were doing like kind of similar stuff. So
nice. I'll check it out.
check it out, some of that work. And
yeah, thank you.
Yeah, you're welcome.
But,
Yeah. Well, I think there is another question in the chat. So it says, what could be a good method for posterior transcription correction? I mean, without access to the original probability matrix. I mean, correction after ASR of a black box model. I would say that one way to maybe help this is to could be like use a NLP task somehow. This task that say maybe this word doesn't make sense here in between these two, I don't know, like these two other words or things like that. But as a language model is already using the ASR, it might be trickier. But I think that could be done. That could be done. That could be a one way to transcribe and also maybe enhance the transcript. This transcript normally they don't produce punctuation or things like that. So maybe like a NLP task post processing that could be also useful for doing that, for enhancing.
Yeah, there's a library named Gramformer that can eventually be used for that. But I've actually never tried to use like this because it's just some libraries for they detect typos and words are misspelled or whatever. It's like it's a grammar correction thing, a bit like Grammarly, but open source. There's one named Gramformer. If it works, that would be interesting to know.
Yeah, makes sense. There is another question from YouTube. I think it's okay.
No, on YouTube, no.
Okay.
So I don't know if there is no more questions. I think we are in good timing. I'm taking the liberty to share the blog from Mile.
Yeah, cool. And the Twitter from Juan Pablo is also very active.
Also from
Oh yeah, I love Twitter. Yeah, actually the people from Speech Brain, they just released like a new. By the way, for like a state-of-the-art models for many different languages. That was like yesterday or two, like Kingawanda, Italian, Swahili, and things like that. So
yeah,
I always post stuff in Twitter.
So yes,
I'm putting the link of the Twitter of Juan Pablo if you guys want to stay up to date.
I will put it. I will put my.
Yeah, thank you. Yeah, so I recommend to follow Mile and Juan. I mean, they are very active and they are quite modest, but they have very cool things to show.
Oh, thanks.
So I don't know, guys, if you have any takeaway message or, well, this is up to you. I mean, we are 7 minutes before ending, but as you wish. If there are no other questions from the attendees.
Yeah, I mean, otherwise, I think as a wrap-up, we're very happy to give this introduction talk. Hope it motivated you to dive into what comes before text is there and how you can leverage speech recognition for that. And all the applications, we only touched on the small set of things that even just speech brain can do. You can do like speech classification for specific emotion recognition. There's really lots of cool stuffs that I think you are now open. So anything you guys are interested in building, also I'd be interested to know a bit more about, to assist. So just feel free also to
reach us
out by email. There's my email on my blog. or you can write to Juan Pablo on Twitter.
Yeah, to Twitter. Yeah.
And
Yeah, be happy
be happy to help and to see if there's anything that comes out of this. And otherwise, I hope it was clear. I hope you guys enjoyed it, that you feel like you've got a better understanding now of the field of speech processing. And see you, until next time. Then with
next year, Summer School.
hopefully physically.
Yeah, that would be great. Physically.
Would have loved to come to Mexico then.
Yeah, so yeah. Keep us there for the next year.
Thank you guys. Yeah.
Thank you to you as well.
So also, if people are looking for PhDs or postdocs, maybe you can ask recommendations to Juan Pablo or Mael.
Yeah, I always there are also a lot of people. I retweet a lot of follow a lot of people who is in this field, machine learning in general, and they are always looking for new PhD students and masters and internships and stuff like that. So it might be nice for you.
And EJAP is doing pretty cool stuff there and always recruiting new PhD students or new master's students.
I think that was one of the main idea of me showing the pictures at the beginning, to motivate you to continue the machine learning, field, whatever, and research, and and just remember that never is too late, because there is some people okay, I am already in my master's degree and I don't have any knowledge about this. I haven't checked this around, and then it's all up to you to invest some time and continue. And sometimes you need to push a little bit, but most of the time you get some reward back. Yeah, that's all from my side. And thank also Esau for the invitation.
Yeah, thanks a lot for the organization.
Thank you, Mike. Thank you.
Yeah.
Okay. Thanks a lot, everyone. Goodbye.
Okay. Thanks, everyone. Bye.
Thank you.
Nice
Bye-bye.
rest of day.